Hello, welcome back to lesson 4, the theorem of uniqueness for limits. This will be a rather short episode as we're going to only go over one theorem and one lemma necessary in proving that theorem. This is the first theorem related to limits as we move forward from simply proving specific limits to proving properties of limits. So let's look at this lemma. The lemma is saying if the absolute value of a minus b is less than epsilon, then for any epsilon greater than 0, a is equal to b, or alpha is equal to beta. So, in other words, what this is saying is that if the distance between a and b is less than any positive integer possible, then a has to be b, or alpha beta. So the proof for this would be to first fix epsilon is to be greater than 0, and you have to suppose that a is not equal to b. And this is just going to be a proof by contradiction, so without loss of generality, we can simply say that b is less than a. So we're going to be doing the following. We're going to set the absolute value of a minus b to equal a minus b. This is true because we know b is less than a, so a minus b is positive, and by the definition of the absolute value, we are going to get the following. And we're also going to choose now epsilon to be a minus b, and you'll see why this is important in our contradiction later. Remembering that the absolute value is strictly positive. So, by assumption, the absolute value of a minus b less than epsilon is equal to a minus b, which implies that, remember, we chose epsilon to be a minus b is less than a minus b, or a is less than a. Right here we have the symbol for contradiction. You can use this symbol or you could just write contradiction. The point is that we have a contradiction of the real set of numbers. The set of real numbers says that any number cannot be less than itself. Like this is a contradiction. No real number can be less than itself. In fact, no number. Well, this only applies to real numbers because we have an inequality, but no real number can be not equal to itself or less than itself. Therefore, a is equal to b. So we have that proof done. Let's move on to the actual theorem of uniqueness of limits, and recalling that a limit can convert. Recall that for f with the basically this is just saying f is a function where the domain is the set A and it yields a real result. I'll write it again, explaining what it is, and recall that for that f, for real f, the limit as x approaches x naught of a real number of f of x is equal to L, which is also a real number if and only if the following definition is true. And we also have if x naught is not a real number. This shouldn't affect our proof too much, as I'll explain what's different, but actually it doesn't matter. So, and remember that we're going to prove that a limit can converge to at most one value. So this limit right here, as x approaches x naught of f of x, converges to L. We're going to try to prove that a limit can only converge to at most one value, or that the limit is unique. The theorem of uniqueness of limits. Let f be a function such that the set of A is its domain, and it yields an output of the real numbers, where A is a subset of the real numbers. So this is how you write a function. A is your set. A is a set, and that set actually happens to be domain of the function. This basically means that it yields, it's a relationship between this set and this set, which is a set of real numbers, which is its output, and A is a subset of the real numbers. So in other words, every element of A is also a real number. So we're calling our definition if the limit as x approaches x naught of f of x is equal to A, and the limit as x approaches x naught of f of x is equal to B, then A equals B. This is the proof. This is the theorem of uniqueness of limits that we're trying to prove. Because notice, it's not possible for A to be different from B. If these two limits, if this limit is equal to that, and this limit is equal to that, A and B actually have to be the same number. So the top can simply be written as the definition, or if you happen to have x naught that's not real, like right here, it wouldn't change much. We would just have either x is greater than delta 1 or x is less than minus delta 1, depending on whether it's plus or minus infinity. And here we're going to write the exact same thing, noticing that again, it doesn't matter if x naught is even real or not, as I'll show later on in the proof. So proof, fix epsilon to be greater than 0. So the absolute value of a minus b, which is equal to the a minus f of x plus f of x, as notice this would just yield 0, minus b is equal to, and why are we adding an fx here? Well, we know already from here that, and I should say, our limit here is a, and our limit here is b. But that, if we do this, we'll just first, reorganize this here, kind of in parentheses almost. And by triangle inequality, we know that the absolute value of a minus f of x plus f of x minus b is less than or equal to the absolute value of a minus f of x plus the absolute value of f of x minus b, which is less than epsilon. In other words, the absolute value of a minus b is less than epsilon. And this is the conclusion because we're going to be working backwards. So by symmetry, we're simply going to flip the f of x and a. It's a property of the absolute value, which implies that the absolute value of f of x minus a is less than epsilon over 2, and the absolute value of f of x minus b is less than epsilon over 2. If you remember from our proving the limits, we can actually do this. This is an idea that we thought of. And we know that both this and this are locally true at x naught by our hypothesis. Remember, we proved that this, which, remember, by assuming that these two limits are true, we assume this premise and this premise, meaning that we can conclude this and this is true. In other words, this is true, we don't have to go any further. And you may say that we have an epsilon here and an epsilon over 2 here. And to that I say, it doesn't matter, because epsilon over 2 is a positive number. Epsilon is a positive number. Either way, if you want here, you can even set epsilon over 2, and let that be your epsilon. It doesn't matter. The point is that it's a positive number. Any positive number, I should say. And that's locally true at x naught by the hypothesis. So we can conclude, essentially, that the absolute value of a minus b is less than epsilon for epsilon greater than 0, any epsilon greater than 0. And by the lemma we proved up here, which says that if the distance between a and b is less than any positive real number, then a has to be equal to b. And we have finished our proof. We have proven that if the limit as x goes to x naught of f of x is equal to a, and the limit as x goes to x naught of f of x is equal to b, then a equals b. And that's the theorem of uniqueness for limits. This is crucial because we can't really work on limits if we know that it's possible that one limit can have multiple answers. We don't have to worry about that anymore, as we've just proved this is an impossibility. Hopefully you guys understood this and it helped you out in some way, whether you're taking a calc test or if you're just studying yourself for your class, real analysis, whatever it may be. Good luck.